Hello and welcome to my very late videos on Continuing Ed Week 5 in Honors Geometry. We are jumping into a new unit this week and next week, talking about surface area and volume, which is super cool stuff. Now, you'll notice that this unit builds directly on the previous unit, and that surface area is literally just an application of area as we look at three-dimensional figures that have multiple surfaces. And volume, of course, is an extension of the idea of finding the space enclosed by certain boundaries. But in this case, we're going to be looking at three-dimensional figures that enclose that space. Thus, we refer to that three-dimensional space as volume. Now, this week, we're going to talk about three-dimensional figures in general, some terminology for them, some interesting features. We're also then going to look at surface area of prisms and cylinders and volume of prisms and cylinders. So we're really going to focus on kind of the foundational building blocks this week, and then next week we'll look at some of the more involved and sometimes difficult cases. Now, with that said, let's talk about three-dimensional figures in general. Now, one of the things you're going to notice, well, you're not reading 11.4, but a polyhedron is a solid that is bounded by polygons that are referred to as the faces of that particular polyhedron. You'll notice, here's an example here of a polyhedron, or of a three-dimensional solid. You'll notice that each vertex is what we talk about as the corners or the points in this particular three-dimensional object. Each edge is the segments that travel between any two vertexes, and each face is a collection of these different edges that bound a particular surface. So they give us a portion of a plane. And there are actually five solids that are really commonly talked about when you start talking about volume and three-dimensional figures in general, and those are called the Platonic solids. Platonic solids are significant in that they have congruent regular polygon faces. In other words, a cube has 6 congruent square faces. A tetrahedron has 4 congruent triangular faces. An octahedron has 8 congruent triangular faces. A dodecahedron has 12 congruent pentagon faces. And an icosahedron has 20 congruent triangular faces. This, if you are a dice player, this is a D20, or a D&D player. This is a D12. This is a D8. This is a D6. And this is a D4. You'll notice these are all dice because Platonic solids, because of the fact that they have congruent faces, end up being symmetric, and they give fair distributions when you roll them, thus producing likely outcomes for every single face. This is why these are so commonly used in the creation of dice, which is really handy. Now, we could go through this whole process, but one thing that you'll learn if you were to do some more investigation into these things is that there is a relationship among the number of vertices in a three-dimensional solid, the number of edges in that solid, and the number of faces in that solid. And actually, this is called Eulers, one of Eulers' formulas in geometry, and he discovered that vertices minus edges plus faces is always 2. To give you an example of this, we will look at the tetrahedron. The tetrahedron has 1, 2, 3, 4 vertices. It has 1, 2, 3, 4, 5, 6 edges. And it has 1, 2, 3, 4 faces. 4 minus 6 plus 4 is, believe it or not, 2. Pretty handy. So, again, this is just an interesting factoid about some of these solids. Now, we're going to talk about some of the solids that we're going to be working with in the course of the next couple of lessons. And what you'll notice is there are different types of three-dimensional figures. So, again, you have your polyhedra, which are solids bounded by polygons, like your prisms, which have rectangles on all the sides. In this case, in this prism, you could also have a triangular prism or a hexagonal prism. Or a pyramid is another example of a polyhedra. And so that is a polyhedron. And then we also can talk about things that are not polyhedra, but are solids, like cylinders, cones, and spheres that have curved edges to them at some point. Now, when you're naming a prism, or you're naming a cone, or a cylinder, or a pyramid, you're going to use the shape of the base in order to give it a name. So right here, we would call this a square pyramid. Why? Because the base of the pyramid down here on the very bottom is a square. So keep that in mind. When you hear me say like, oh, look, this is a hexagonal prism, that means it has a hexagon on the base, and then it has, and then it's a prism in shape, which means it has two bases across from each other, and then all the sides formed as rectangles. Now let's go ahead and name these again. Let's say we're talking about things are polyhedrons. Again, yes, this would be, because it's made of all polygons, and this would be a square. Again, name it by the base. Pyramid, by its shape. Again, a pyramid, to be clear in its definition, has a polygon base, and then it has all of its edges from that base sloping to meet at a singular point. This here would not be a polyhedron because we have a curved surface here, which means we're not going to be able to make that out of flat polygons. This one would be over here. Notice we've got a triangle and a triangle, so there's our triangular bases. So it's triangular. And then in this case, it would be a prism. Prism because we have two bases parallel to each other, and they are connected by vertical edges. Okay. Again, there's a lot of different features here as we're talking about terminology and just general ideas with these three-dimensional figures. But something else you'll hear commonly, especially if you look into really the biology world or you look at the production world, are things that are called cross-sections. A cross-section is really just like a slice out of a particular three-dimensional solid. And you'll notice you can slice that cross-section anywhere as long as you're using a flat plane to do so. Now, there may be strategic reasons for where and why you use a cross-section, but just keep in mind that's what that process looks like. Cross-sections can also make different kinds of shapes depending on the angles that they cut them, right? So here again, we would see, for example, a cross-section, that creates a pentagon. Over here, we would see a hexagon. And here we would see a circle. All right. Now, the other type of solids that we'll introduce are those that are cylinders. So a cylinder is a three-dimensional figure that's formed by rotating a 2D shape around an axis. The line which it rotates is the central axis. And again, a lot of times whenever we have anything like this, it's going to create something with a curved edge. And you'll be able to see what's going to happen in a lot of these situations. So for example, if we were to take this particular shape and rotate it around, we would end up with a cone. We would have the kind of triangular shape from the side, but it would be wrapped all the way around, which would give us a shape like that. Over here, we'd have a cylinder. We'd have a rectangular shape from the side, wrapped all the way around, thus giving us a cylinder. And here, we'd have a sphere. We have a curved shape from the side, wrapped all the way around. So again, this is just kind of more of a visualization of three-dimensional solids. I'll be honest, this lesson may not be as useful to some of you that are more familiar with these solids than others. But again, it gives you some ideas, some terminology, so that we can reference different vertices, edges, and faces, If Platonic solids are mentioned, you're aware of what those are. You're aware of the distinction between polyhedra and non-polyhedra. And again, those are 5 major types of solids: prisms, pyramids, cylinders, cones, and spheres. And then we talked a little bit about cross-sections, as well as how cylinders are defined. And really, folks, that is about as much as I can give you. Yeah, so hopefully this helps you get a little visual before we start jumping into really the more meaty math. But thanks for tuning in, and I'll see you in the next video.